For the properties of solutions activity, we begin by seeing again what the common concentration units are that we use in chemistry. Molarity, symbolized with a big M, is defined as moles of the solute per liter of solution. Molality, symbolized with a little m, is defined as the moles of the solute divided by kilogram of the solvent. Mass percent is defined as the mass percent of component A within a mixture is the mass of A divided by the total mass, so the mass of A plus the mass of B plus the mass of C, however many components there are. And then since it's percent times 100, so percent A is mass A divided by total mass times 100. The mole fraction, symbolized with that, looks like an X, chi, is for component A, defined as the moles of A divided by the total moles. Often we don't multiply by 100. We keep it as like a decimal quantity. Now we deal with the various equations that we use in this activity, and all of this material is Chapter 11, so be sure to review your Chapter 11 lecture notes. So, Henry's law. Henry's law is what we work with when we have gas above a liquid and we're figuring out what the concentration of the gas within the liquid is. And that concentration C is equal to K times P. So C represents the concentration of dissolved gas within that solution. K is Henry's law constant. And P is the pressure of the gas above the solution. So, sample problem. Calculate the solubility of O2 in water at sea level at 25 degrees Celsius. So this is how there is oxygen in water for the aquatic life, the plant life, animal life in the water. The partial pressure of O2 at sea level is 0.21 atmospheres. The Henry's law constant for O2 in water is 0.0013 moles per liter atmosphere at 25 degrees Celsius. So we're after concentration. Concentration we can think of as equivalent to solubility. So concentration is equal to K, 0.0013 moles per liter atmosphere, times P, 0.21 atmospheres, equaling to 2.73 times 10 to the minus 4. Units are moles per liter because we noticed that atmosphere cancels out, or we could write that as molar. Our next one is working with vapor pressure of solutions. So when we have a solute in a solution, it affects the vapor pressure of that liquid. So if we think of the vapor pressure as the pure liquid versus the vapor pressure of the solution, they're definitely different. The vapor pressure of the solution is a little less than that of the solvent, at least typically. And that is given by what's called Raoult's law, this equation 2. So the vapor pressure P of the solution SOLN, so P of solution is chi of the solvent times the vapor pressure of the pure solvent, that's what's meant by that P naught solvent, plus chi of the solute times P of the pure solute, where chi solvent is the mole fraction of the solvent, chi solute is the mole fraction of the solute, P naught solvent is the vapor pressure of the pure solvent, P naught solute is the vapor pressure of the pure solute. That would only apply to volatile solutes. Many solutes, like imagine sugar dissolved in water, many solutes have basically zero volatility, so their contribution to any kind of pressure is going to be negligible. If the solute does not produce a vapor, it is non-volatile, then P naught of the solute becomes zero, and Raoult's law simplifies to equation 3. P solution equals chi solvent times the P naught of the solvent. That's the more common version of the equation you will find you use. So here's a sample problem. Calculate the vapor pressure of a solution made by dissolving 651 grams of ethylene glycol, C2H6O2, a non-volatile solute with a molar mass of 62.07 grams per mole, in 1.50 kilograms of water, where we're given the molar mass of water to be 18.02 grams per mole at 90 degrees Celsius. The vapor pressure of pure water at 90 degrees Celsius is 525.8 millimeters of mercury. Okay, so step one, let's actually see our equation. We have a non-volatile solute, so we are using this equation 3 version of Raoult's law. The vapor pressure of the solution is chi of the solvent times the vapor pressure of the pure solvent. So we have to figure out what chi of the solvent is, and that's the mole fraction of the solvent. So we have to get the moles of the solvent and the moles of the solute, and take the moles of the solvent and divide by the total number of moles. So for the solute, we have 651 grams of ethylene glycol divided by its molar mass, 62.07 grams per mole. Notice the unit gram cancels out. Now we have moles of ethylene glycol, 10.5 moles. 1.50 kilograms of water. We first convert from kilograms to grams, and then we use the molar mass of water, grams in the bottom. So we end up with 83.2 moles of water. Then we find the mole fraction of the solvent. So bear in mind, it's not the solute, it's the solvent. So chi of water is the moles of the water, 83.2, divided by the moles of the water, 83.2, plus the moles of the ethylene glycol, 10.5. And that comes out to be 0.888. Notice that chi, the mole fraction, is unitless. So now we use Raoult's law to find the vapor pressure, the one that we're after. So the vapor pressure of the solution is chi of the solvent, 0.888, times the pressure of the pure solvent, 525.8 millimeters of mercury, or 467 millimeters of mercury. So it's a little bit lower than that of the pure water. The Van't Hoff factor, that's symbolized a small case I, and it is the number of moles of particles produced in solution per mole of solute that dissolves. So it has to do with how many moles you start with versus how many moles those break into. If we're dissolving sugar in water or glucose in water, those don't break up into more particles than we begin with. So if we dissolve 1 mole of sugar in water, we get 1 mole of sugar dissolved. But if we dissolve an ionic compound, it does, and it's a soluble one, it does break apart into at least 2 particles per 1 original unit. So NaCl, the Van't Hoff factor is about 2 for that one. It is measured experimentally to be actually 1.9, but unless we're told that as we need to go about solving a problem, assume it to be 2. For calcium chloride, Unless we're told otherwise, we assume the Van't Hoff factor is 3. Okay, the Van't Hoff factor comes up in the boiling point elevation, freezing point depression, and osmotic pressure. So the normal boiling point, remember normal means at sea level, 1 atmosphere. So the normal boiling point of a solvent is calculated through equation 4. That would be, we calculate, well, let's see, a non-volatile solute will elevate the normal boiling point of a solvent through equation 4. So that's giving the amount that the boiling point goes up by, delta T sub B. So delta T sub B is equal to I times Kb times M of the solute, where delta T sub B is the change in boiling point. It's the T sub B of the solution, so the boiling point of the solution minus the boiling point of the pure solvent. So the solution boiling point is a little greater than that of the pure solvent by the addition of that solute. I is the Van't Hoff factor. K sub B is the boiling point elevation constant, which depends upon the solvent. M solute is the molality of the solution. When a solute is dissolved in a solvent, the freezing point of the solution is lower than the freezing point of the pure solvent. So boiling point is raised, freezing point is lowered by the addition of a solute. So delta T sub F equals I K sub F M of the solute. So it's very similar to equation 4 in how it looks, but of course delta T sub F is describing the change in freezing point, the freezing point of the pure solvent minus the freezing point of the solution. I, same Van't Hoff factor. K is the freezing point depression constant for the solvent. So it has to do with, just like the boiling point one does, the solvent, but this is the freezing point constant. So it would have a different numerical value than the boiling point constant. And then M solute is the same. It's the molality of the solution. Here's a sample problem. What is the boiling point of a solution containing 0.144 grams of eugenol, which is C10H12O2, a non-electrolyte that is the active ingredient in cloves? Molar mass is 164.20 grams per mole in 0.0100 kilograms of benzene. Benzene has a normal boiling point of 80.10 degrees Celsius and a boiling point constant of 2.53 degrees Celsius kilograms per mole. Okay, so step 1, as the equation involves molality, find the moles of solute and kilograms of solvent. Alrighty, so we take those 0.144 grams of eugenol, we divide by the molar mass of eugenol, and we get 0.000877 moles of eugenol. The molality then is the moles of the solute divided by the kilograms of the solvent. We're already given the mass of the solvent, the benzene, to be in kilograms, so we're set there. So we put the moles solute, 0.000877 moles of eugenol over 0.0100 kilograms of benzene, and we get 0.0877 moles per kilogram. So that's the molality. Step 2, find the increase in boiling point, the boiling point elevation. So now we're using our boiling point elevation equation, delta T sub B equals I K sub B times molality. So the Van't Hoff factor is 1. How do we know that? Well, this eugenol, we're told, is a non-electrolyte, so we assume it to be a molecule, much like sugar, that stays together. It's soluble, but it does not break down into various components. So I is 1. In fact, unless it's an ionic compound and unless we're told otherwise, we pretty much have a molecule and we assume I is 1. So K sub B, we're given to be 2.53 degrees Celsius kilogram per mole, and then we multiply by the molality, 0.0877 moles per kilogram. So we see kilograms cancel, moles cancel, and we're left with degrees Celsius, 0.222 degrees Celsius. So that's the amount that the boiling point goes up by. So we find the boiling point then of the solution. Solutes elevate the boiling point as we talked about. So delta T sub B is T sub F of the pure solvent minus T sub F of the solution. So T sub F of the solution is T sub F of the pure solvent. Wait, that should be T sub B. Okay, so it should read delta T sub B equals T sub B of the pure solvent minus T sub B of the solution. So T sub B of the solution should be T sub B of the pure solvent plus delta T sub B. So we have 80.10 degrees Celsius plus 0.222 degrees Celsius, and we get 80.32 degrees Celsius as the new boiling point with that solute. Notice that delta T sub B increases as the molality increases. So when we have a more concentrated solution, we get more of a boiling point elevation. Our last section is osmotic pressure, and when a pure solvent and solution are separated by a semi-permeable membrane, solvent molecules will pass through the membrane but not solute, resulting in a decrease in the volume of the pure solvent and an increase in the volume of the solution, and that will just occur naturally. So imagine a U-tube where we have a semi-permeable membrane in the middle. We put pure solvent on one side and a solution containing that solvent on the other side. The solvent will move over, some of the solvent will move over to the solution side, causing the solution side to have a larger volume. And the amount of pressure it takes to stop that spontaneous osmosis from occurring is the osmotic pressure. And it is symbolized with the capital symbol pi, and it equals I times M times R times T. So the pi is the osmotic pressure, often in atmospheres. It depends on the gas constant used. I is the Van 't Hoff factor. M is the molarity. R is the gas constant. Often, if we're working with pi in units of atmospheres, we're using the value for R to be 0.08206 liters atmospheres per mole Kelvin, and the temperature is in Kelvin. So notice that as we increase the molarity, that is, we have more solute dissolved, we have a greater osmotic pressure. Here's a sample problem. Calculate the osmotic pressure of 0.0575 molar calcium chloride solution at 25.3 degrees Celsius. So first off, we convert the Celsius into Kelvin by adding 273.15. We get the temperature in Kelvin to be 298.5 Kelvin. The Van 't Hoff factor we assume to be 3 because we have an ionic compound that breaks into 3 ions. So we have pi equals I M R T. We have 3 times 0.0575 moles per liter times 0.08206 liters atmospheres per mole Kelvin times 298.5 Kelvin. We see that liters cancels, moles cancels, and Kelvin cancels. We're left with units of atmospheres. We have 4.23 atmospheres. So that is the end of our introduction. And to do these problems that are part of the report, of course, you can skip the pre-activity. Look back at the introduction as you need to. Also, look at your Chapter 11 handout notes because they contain a lot of problems that are perhaps similar to ones you'll find in here. So in problem 1, we're working with those different units of concentration: molarity, molality, mole fraction. Number 2, we're asked about solubility, so think of similar properties, polar, nonpolar type stuff. So number 3, we're working with Henry's constant. Number 4 is a boiling point elevation type problem. Number 5, we're working with the freezing point depression equation. Number 6, osmotic pressure. And number 7, the vapor pressure of the solution, Rayout's law. And number 8 is also a vapor pressure problem. Now, some of these are a little tougher than ones in the introduction, but they would be similar to problems that you're assigned in the homework for Chapter 11, also similar to problems that we have done in the Chapter 11 handout. Alrighty, so when you are done with this, double check, make sure everything looks good for you, and then scan it, preparing it as a PDF file, and submit it.